All right, good evening, ladies and gentlemen. Welcome to the 2008-2009 Science Technology Society lecture series, the Linus Pauling Memorial Lectures. My name is Terry Bristol. I'm the president of the Institute for Science, Engineering, and Public Policy, and it's an institute that organizes this, but it is also with the help, great support of our partners and co-sponsors. So my first thing here is to thank them, and our major, those of you who are here regularly, our major and for several years now corporate co-sponsor is Mentor Graphics Corporation. So I want to say a big thank you to them, particularly. And then I mentioned also Oregon Episcopal School. Good people, yes. FEI companies, our electron microscope, great company. The Oregon University System, which starts with the Chancellor, matched by Portland State University, University of Oregon, Western Oregon University, and also Portland Community College, Mount Hood Community College, Clark College in Vancouver, and then down at Oregon State, ONAMI, which is the nanotech research thing that's going to provide and create all the jobs for all you young people here in the next thing. FLIR Systems, which has been creating jobs for a lot, great company. Lewis and Clark College, Pacific University, and thank you to the Oregonian. Also, then, that's all the direct co-sponsors. And then Mentor Graphics, besides Mentor Graphics Corporation, Mentor Graphics Foundation also gave us a grant, which is what sets up the matching funds and so forth for probably 1,000 students and whatever that are here from the Oregon University or Oregon school systems. So thank you to Mentor Graphics Foundation. Final check for your cell phones. Make sure your cell phone, oh, did I turn my cell phone off? No. So double check that. And then when Dr. Greene's done, there's a standard 3 mics, 1 up above, 2 in the aisles, and you just go to those. And he will answer all the crucial, if there's anything that you don't understand from his talk, which is probably, he might do that. And what else might I have forgotten? Oh, I just mentioned the OSU Brain Series is coming up, starting up. And also, I would mention some of you who are really, the guy who's coming in January, it's in your program, I'm really excited about this thing about design and so forth, and it's Terrence Love, and it's going to be really cool. So he doesn't have that much exposure, but you're going to love it, and it's very, very important to where the world, intellectually, where the world's going, and the economy and everything. So anyway, I want to encourage you to come to that. So with that, I'm going to, it's my pleasure to introduce Dietrich Belitz, I'm sorry, I was pronouncing it wrong here. He's a professor of physics at University of Oregon who is going to introduce Dr. Greene.
Good evening and welcome. And it's my pleasure and privilege to introduce a distinguished colleague of mine tonight, Dr. Brian Greene. The topic of the lecture is cosmology, which is a very old subject. We know from some of the oldest records in history that throughout times people have wondered about cosmology. They observed the place around them, they looked at the sun, the moon, the planets, the stars, and later on they found there were more objects, there were galaxies, there were galaxy clusters, and so they wondered naturally where do all these things come from, and how do they develop, and why are they there? Now, another very old question has to do with the nature and the constituents of matter and of light. What is matter? What is light? What is time for that matter? Okay. And people very, very early on asked questions like, if I take a rock and I keep dividing it into smaller and smaller pieces, what will happen? Will at some point I hit a smallest constituent? Or will it just keep going, dividing forever? Is it a continuum? Or is it discrete? So initially, these were philosophical questions, but then over time, they became scientific questions, and they could be checked. And so it turned out that if you keep dividing that rock, ultimately you come to atoms, and you can take them apart, and there are nuclei and electrons, and you can take the nuclei apart, and you get to quarks and gluons and so on. So is there an end? Well, we still don't know, but string theory proposes that ultimately matter and light and everything we know of can be reduced and understood as vibrations of the fabric of space-time itself. Now, one really very surprising thing that happened in the 20th century is it turned out these questions about the very large structures around us, the universe itself, and the questions about the very small stuff, the atoms and quarks and electrons, they are closely related, which is not at all obvious at first sight. It's got to do with a discovery Edwin Hubble made, who found that the universe is not static, it's actually expanding. And so if one follows that expansion back in time, then one finds that some 15 billion years ago, all of the matter and all of the light and everything we know exists in the universe was confined in an extremely small space, and therefore it was very, very dense and very hot, and everything was disassembled into its basic constituencies. And so that's where the relation is. Now, our speaker tonight, Dr. Brian Greene, has written a lot of very influential technical papers on this subject, but that's only part of the reason why he's here tonight. He's also very, very talented as a publicizer of science, and he's very good at explaining science to both scientists and non-scientists. He earned a bachelor degrees from Harvard University in physics and a PhD in physics from Oxford, where he went as a Rhodes Scholar. And he was associated with various universities, and for the last 12 years, he's been a professor of physics and mathematics at Columbia University. And tonight, he's going to talk about cosmology at the frontier. Brian Greene.
So, are there any questions? Thank you for that warm introduction. It's a pleasure to be here. And it's often when I go out and speak about science, it is to audiences like yourself, adults who have a passion for the subject. But every so often, in fact, a little bit more recently than in the past, I've been giving lectures or holding discussions with younger audiences, which has been a very interesting experience. A few months ago, I was asked, in fact, to speak to a first grade class. And perhaps I shot a little high. I asked them a few questions in string theory. No, I wanted to give them an opportunity to show me what they'd learned in math, so I asked a question, how do you do 3 into 6? This little girl raises her hand, I pick on her, she goes to the board, writes this big 6, and puts a 3 into it. Which wasn't the answer I was looking for, clearly, but it was a wonderful moment, because it really shows how, when we're young, we have this uninhibited, unabashed willingness to just explore, to go forward into the unknown. I mean, there's another example of that experience I had with my own son. He's 3.5 now, but when he was 2.5, I was telling him some bedtime stories, and no doubt I get a little carried away. Telling him things about spaceships going near the speed of light, all this kind of stuff. I don't know how much he's taking in. And then he turns to me and says, Dad, the speed of light, what about the speed of dark? Again, a good example of how we start. And perhaps the best example of all is not mine, but a story that the great educator Ken Robinson told, and I was fortunate enough to hear it not long ago. He tells a story of a second grade class where all the kids are at their little desks, they're drawing pictures, and the teacher goes up to one little girl and says, "What is it that you're drawing?" And she says, "Well, I'm drawing the face of God." And the teacher says, "Really? How are you going to do that? Nobody knows what God looks like." And the girl shoots back, "In a minute they will." Now the thing is, the great scientists are the ones who never lose that childlike wonder, that childlike, uninhibited ability to just go forward. It can be a very uncomfortable thing being a scientist. It's a life of uncertainty. Field I've been working on, string theory that was mentioned, I've been working on it more than 20 years. I don't know if it's right or if it's wrong. It's a very uncertain, precarious in some sense life that you lead. But that's really what it takes. And what I'd like to do tonight is tell you one particular story that I think is the most magnificent one in science, or at least certainly in physics. You heard a little bit about it in the introduction, the story of cosmology. And the scientists that we will encounter in this story are just the ones who've never lost that kind of childlike sensibility. Now, cosmology is a wondrous story. Throughout recorded history, across cultures, we have struggled to find our origins. That's how we anchor ourselves, some sense of where we came from, how the universe came to be. Now, the scientific story of cosmology is a relatively new one. It really begins in the early part of the 20th century when Albert Einstein is struggling to figure out how the force of gravity works. He knew, as all scientists at that time did, that Isaac Newton, 250 years earlier, had written down his famous equation for the force of gravity, an equation that we teach to our students around the world today. But Einstein, at one and the same time, recognized the power of Newton's insight because it could make predictions for where the moon and where the planets should be. But at the same time, Einstein was puzzled by what Newton wrote down. He was puzzled by the kind of question that a 5-year-old asks. But he was the kind of scientist who was willing to ask that question. He asked, how is it that gravity works? How is it that the sun, 93 million miles away from the Earth, somehow keeps the Earth in orbit? How does it do that? And he spent 10 years trying to come upon the answer. And as some of you know, he began that journey by going to the Principia, the book that had all the results in math and physics that Newton found in his lifetime, to try to figure out what Newton was thinking about how the force of gravity works. So he goes over to the Principia. You know the story. He opens to letter G, finds the force of gravity, goes a little bit further down for the subheading M, the mechanism by which gravity operates. And there he finds a surprise. Because Newton says, I don't know how gravity works. He says, I've been able to write down this equation that governs the influence of gravity, but I don't know how it actually exerts that influence. And in his own words, he said, to the answer of that important question, the mechanism by which gravity operates, he said, I leave it to the consideration of the reader. Einstein was the kind of reader who could not simply read that and read on. And that's what he spent 10 years on. And by the end of his journey, by 1915, he gave the world a new theory of gravity called the general theory of relativity, and it lies at the heart of our understanding of cosmology. So I'd like to tell you a little bit about the general theory of relativity. No doubt this is a review for some of you, but just to get us all on the same page. Einstein said, to understand how gravity works, you need to recognize that space and time themselves have a real existence. They can change their shape. They can warp and curve. And in fact, he said that if you imagine space as if it were a big, huge rubber sheet stretched in front of us, and if you imagine an object in space like the sun, when that object is in space, it acts almost like a rock that would sit on top of that rubber sheet, causing the sheet, space itself, to warp and curve. And it's those warps and curves in space, he said, that communicate the force of gravity. Let me show you what I mean by that. So if you could just bring down the lights, if you would. So out there in space, this grid-like icon is what we'll use to denote space. That's 3D space, a little hard to picture. Let's go to a two-dimensional version that captures all the ideas. If nothing is in space, Einstein says it's nice and flat, as we see here, but when the sun appears, the fabric curves. It warps. Similarly, around the Earth itself, space is warped. And look at the moon, because this is the point. The moon is kept in orbit because it's rolling along this valley in the curved environment that the Earth creates. That, Einstein said, is how the force of gravity is communicated. And if we pull back and take a look at the Earth itself, it too is kept in orbit by rolling along a similar valley in the curved environment that the presence of the sun creates. That, you can bring the lights back up, is how gravity works. Now, Einstein published this general theory of relativity in 1915, 1916. And little by little, the world of science got word of the insights that Einstein encapsulated in the general theory of relativity, and other scientists began to think about the implications of this new theory of gravity. In Germany, Karl Schwarzschild, who at the time was on the Russian front in the German army fighting World War I, gets hold of Einstein's manuscript and solves Einstein's equations for how space would be curved outside a spherical body, and in so doing, he discovers the idea of black holes. Interesting story in its own right, not one that we're going to cover here tonight. Rather, the insight that I'd rather focus upon is one that comes from this fellow over here, a Belgian priest with the unusual distinction of also holding a PhD in physics. And he began to think about Einstein's general relativity and approached Einstein in 1927 and informed Einstein that when you apply the general theory of relativity not to the sun and the earth, but rather to the entire cosmos, there's a fantastically interesting conclusion. He found that the equations of general relativity, when applied to the whole universe, implied that the universe should be expanding. It should be growing over time. Everything should be rushing away from everything else. Now, when he told this to Einstein, Einstein said, "Your mathematics is correct, but your physics is abominable." And he said this because Einstein was already familiar with this conclusion from general relativity. In his own work, he had come to that conclusion, and he'd also learned about it from this fellow over here, Alexander Friedmann, Russian physicist. Now, when Einstein encountered this idea that the universe should be expanding according to his equations of general relativity, he recoiled from that conclusion. As everybody knew, the universe was eternal, static, unchanging. You look up on a nice dark night, you see the stars, they're not moving. So on the largest of scales, the universe should be static and eternal. Einstein was rather upset that his equations were not compatible with those observations. So what did he do? He went back to the equations and he modified them. He changed them. He introduced something that no doubt many of you are familiar with. He introduced something called the cosmological constant, a new term in the equations of general relativity, which from the point of view of its physical implications is quite easy to describe. Ordinary gravity pulls things together, right? It tends to drag things together. Now, if you want a static situation, an unchanging situation, you need all of the forces to balance, right? If you're looking at a tug of war, if one side is pulling and the other side is not, certainly the rope is going to move. But if the rope is static, it means that one side is pulling with exactly the same force as the other, but in opposite directions, and that way yielding a static game of tug-of-war. Einstein took that idea and recognized that if gravity is attractive, ordinary gravity is attractive, and you want a static, unchanging universe, you better introduce something that can push outwards, that doesn't just pull inwards. And he found a way to do that in his general theory of relativity. This cosmological constant, as the name goes, was able to exert a kind of repulsive gravity, an outward pushing gravity that would counter the ordinary attractive pull of gravity, allowing for a static universe. Now, that allowed him to breathe easy because he thought the universe was static. But in 1929, all that changed. Because in 1929, this fellow over here, Edwin Hubble, who was an American astronomer trained at Oxford using the 100-inch Mount Wilson telescope, studied the motion of distant objects in the heavens. You could bring the lights down to get a little better contrast on that. And he found, upon studying those distant objects, that indeed they were not static. They were moving. He found that everything, in fact, is rushing away from us. He found evidence, indeed, that the universe, you can bring the lights back up, was not static, as Einstein thought. It was expanding. Now, the story goes that at that point, when Einstein heard this information, that the cursory observations that had convinced him that the universe was static were wrong, that it was expanding, the story goes that he said the cosmological constant, its introduction into the equations of general relativity, is the greatest blunder of my life. Now, you can understand why he might say that. If he had trusted his own equations, he would have predicted that the universe was expanding. One of the deepest insights about the nature of reality, he would have predicted it a dozen years before it was actually observed. The reality is, though, for reasons I'll explain in a moment, it's unclear that he actually ever really called it his greatest blunder. In fact, when you look carefully at the literature, he had a very sensible attitude toward the cosmological constant. These observations convinced him that it wasn't a static universe, but he had the prophetic insight, as we will see as we head ever closer to the present, to recognize that it would only be observations, very detailed observations of the heavens, that could determine whether or not there is an anti-gravity happening out there. And in many ways, as we will see, the cosmological constant is a sub-theme in this discussion of where we are at the frontier of cosmology, because by the time we will conclude tonight, we will see it make two reappearances in the history of the subject. Be that as it may, once Hubble recognized that the universe was expanding, it didn't take much to recognize that if it's expanding today, that means that in the past it was smaller and smaller and smaller, and therefore, as Lemaitre had tried to convince Einstein years before, the universe, presumably, according to the equations, began as a really dense, tiny nugget, which, through a big bang-like explosion, if you will, grew in size, pushing everything apart, and we are currently living through the aftermath of that primordial exploding atom, as Lemaitre called it. Let me just show you a quick visual on that, if you could bring the lights down. So according to these ideas then, the universe begins, goes through this Big Bang-like explosion where it's not only matter but also space and time themselves are flung outwards, causing the universe to grow ever larger, and as it grows larger, as we will discuss, it cools down, and as it cools down, structures can begin to form, the kinds of things that you'd see if you looked out in a nice dark night sky, stars and galaxies. Now, bring the lights back up. This was a great moment in the history of cosmology, an unexpected insight that the universe is expanding. And it led others to try to refine the picture of how the cosmos went through its evolutionary stages from the beginning until today. And one of the earliest people to try to think about a more detailed version of this Big Bang theory was a fellow named George Gamow, a Russian physicist, a hulking, 6-foot-tall Russian physicist who was as fun-loving and hard-living as he was quick-witted. He wanted, for instance, to get out of Russia. He wanted to escape the Iron Curtain in the 1930s, so with his wife, he went in a kayak and tried to row across the Black Sea. And the only staples he actually took with him were a whole assortment of fine chocolate and brandy. Now, they rowed along for 36 hours, but the weather got a little bit rough, and ultimately they were picked up by the Russian authorities. And Gamow somehow was able to convince the authorities that he was at sea conducting some physics experiments. So he survived that particular episode. Later on, not too much later, he was able to escape and actually settled at Washington University in St. Louis. But he was a real jokester, a kind of a prankster, had a real silly sense of humor. For instance, just to give you an example, he was writing a paper with one of his students whose name was Ralph Alpher. And he realized that if he could convince this fella over here, Hans Bethe, who was a future Nobel laureate, if he could convince Hans Bethe to put his name on the paper, even though Bethe had nothing to do with it, then the author list would be Alpher Bethe Gamow. And Bethe agreed for reasons that are a little bit unclear. That sort of gives you a sense of the kind of character he was. And here's the thing. He did some real wonderful, serious science. I mean, he was working with these two students over here, Robert Herman and Ralph Alpher, and you can sort of see they made this little cartoon where Gamow is sort of a genie coming out of this primordial bottle. But in any event, they started to think about cosmology, this Big Bang idea, and realized something quite stunning. It's a very simple but powerful idea. They realized that if in the beginning the universe was very small and very hot, then as it expanded and grew, they realized it should cool down, right? That's actually a familiar idea. Think about it in reverse, right? You know when you take a bicycle pump and you're pumping air into an inner tube, you realize that when you feel the inner tube, it gets kind of hot. And it gets hot because the energy that you were using to pump the gas in is going into the motion of the gas molecules. They're moving really fast, so it all heats up. Now, the reverse of that, a compression yielding heat, the reverse of that is that an expansion would cause temperature to drop. So they realized that there should today be residual heat left over from the beginning. They called it the background radiation. Heat left over from the beginning that should be all around us, suffusing all of space. A bath of photons, a bath of radiation that we are all immersed in. And that's a really stunning idea. It suggests that there is a relic of the Big Bang that we have access to, that's all around us. And they did some calculations to figure out what the temperature of this background radiation should be. They came to the idea that it should be pretty cool by today, about 5 degrees Kelvin, their rough calculations revealed. And they thought this was a very exciting discovery. And they tried to convince their colleagues, not only that it was exciting, but that experimentalists should try to look for this radiation that should be all throughout space. Thing is, they could not convince anybody to take it seriously, and they couldn't convince anybody to undertake the experiments. And there are really two reasons for that. Number one, in the 1940s, cosmology was still a backwater of science. It wasn't in vogue the way quantum theory was, for instance. But I think another side of it was that because Gamow was such a prankster, people just didn't take him as seriously as they should have. And this really came back to haunt him and his students because basically people just ignored their paper and forgot about it. Now the thing is in science, when there's some fundamental discovery, somebody may get there first, but if nobody acts upon it, somebody else is bound to come along. And indeed in the 1960s, years later, Robert Dicke and Jim Peebles at Princeton went down exactly the same intellectual pathway, coming to the conclusion that the universe should be filled with this cosmic background radiation. Now the difference was, Dicke was a wonderful theorist, but also a fantastic experimentalist, so he could begin the process of looking for this background radiation himself. And together with some students, they began to build the equipment to look for it. But midway through their planning stages, they got what is considered the most important phone call in the history of cosmology. I'm not sure that distinguishes the call that much. But in any event, they got a phone call from these guys 30 miles down the road at Bell Labs. They had been fiddling around with a communications antenna that you see in the background, and they had found that no matter what they did to this antenna, no matter how they tried to fine-tune it, there's always this background hiss that it was picking up. They did all sorts of things. They even went into the antenna and noted, as no doubt some of you are familiar, that there was some white matter contaminant, bird crap what was in there. So they go in, they clean it all out, but still the hiss remained. Now they then caught word through an interesting grapevine of individuals who were aware of what Dicke and Peebles and company were doing at Princeton. They heard about this possibility that there might be background radiation. They call up Dicke and they explain to him what they have seen with their antenna, and Dicke hangs up the phone and tells his students, we've been scooped. They have found the background radiation. Now it's very interesting because these individuals, when they wrote their paper, really didn't ever mention the word cosmology. They simply reported on the observation that their antenna was seeing some hiss. There was a companion paper that Dicke and colleagues wrote which explained the cosmological significance of what it is that they had found. Neither paper referred to the earlier work of Gamow and his students, and the Nobel Prize in Physics was won by these individuals here, something that Ralph Alpher in particular, understandably, could never get over. He had actually discovered this first decades before anybody else, but that's sometimes what happens in the world of physics, the world of discovery. Now, since this discovery of the background radiation, it has been measured with fantastic accuracy. John Mathers, George Smoot, you may be familiar, recently won the Nobel Prize for their measurements in 1992 of properties of the background radiation. I'd like to show you just a little bit of data, which is, to me, quite wondrous. And what I'll show you here is a theoretical curve. You don't need to know exactly what this curve is, but it's a mathematical calculation of the properties of the purported radiation that the Big Bang Theory predicted. And it tells us how intense the radiation should be at various wavelengths of light. And what I'll then show is, in little red circles, the measurements, the data. And we'll see that there is spectacular agreement. If you can bring the lights down on this. So here, coming up in a second, is the theoretical curve predicted by mathematics based on Einstein's general relativity and this understanding of the Big Bang application. And then the actual measurements look like this. Kind of spectacular. Spectacular agreement between our theoretical understanding and what you actually see when you look out into the universe. So you can bring the lights back up. So this, by the 1960s through the 1990s, was a real spectacular success story for our understanding of cosmology. Man, think about it. We're these little tiny beings walking around on this nondescript star around this ordinary galaxy, which is one of hundreds of billions in the universe. And yet we've been able, through mathematics, through thought, through experiment, to figure out features of the universe that were laid down at the moment of creation. But there are still other questions to be addressed. And a particular individual whose name is Alan Guth, in the early 1980s, took up one of the remaining questions. And there are many ways of motivating Guth's work. But perhaps the most direct way is again to ask one of those childlike questions. If there was this primordial beginning where things were very dense, what is it that caused that outward motion? The Big Bang theory actually was completely silent on that because Einstein's mathematics, if you try to push it back all the way to time zero itself, Einstein's mathematics encounters what we call a singularity. Now, singularity is a fancy way of saying we don't know what the heck is going on. The math just breaks down when you try to push it all the way back to time zero. The conditions are just so extreme, so hot, so dense, that the math can't cope with that environment. So the question, in essence, that Guth was asking was, what banged? Did it bang? Was there really a Big Bang, and what was the cause of that primordial outward burst? He began to think about this question very carefully and came upon an interesting realization. If you're going to have an outward burst, you're going to need something, obviously, that doesn't pull in like ordinary gravity. You're going to need something that pushes outward. That should ring a bit of a bell. You may recall about, 12, 13, 15 minutes ago, we were discussing Einstein and his cosmological constant, this outward push that he introduced into the laws of general relativity to counteract the attractive pull of gravity to yield his desired static cosmos. Guth came to the realization, although he didn't initially frame it in this language, he wasn't really inspired by Einstein's work, but this is a perfectly sensible retelling of what actually was going on. He came to the recognition that you could have a version of the cosmological constant that would give you an enormous outward push if the number was big enough. And he found, spectacularly, a way that that outward burst would only last for a tiny fraction of a second. So he's able to take the anti-gravity that Einstein had identified, turn it on for a brief moment, causing the universe to balloon outwards, and the rest of the expansion follows from that. Now that was a wonderful idea. It's called inflationary cosmology. And when you actually look at the numbers involved, they are really stupendous. In his approach that has been refined by many individuals, the universe grows by at least a factor of 10 to the 30 in as small a time as 10 to the minus 30 seconds. Fantastic, spectacular outward growth, giving rise to the expanding cosmos. Now, in the years after this idea, this inflationary cosmological idea, people again began to think about it in great detail, and they realized that there was, in principle, a spectacular implication of this outward burst. They realized that if space were to expand by such a huge factor, what might happen is that tiny processes from the quantum realm, which are usually too small to be seen, might themselves be stretched out with the huge expansion of space, in some sense allowing quantum physics to be brought into the macroscopic world. I think an analogy captures this idea particularly well. Imagine that I have a balloon with no air inside of it, and I have a really fine-tip pen, and I draw a little message on the balloon, too small for you to see. I then blow air into the balloon, and as the balloon's surface expands, my message grows and it becomes large enough for you to read. A variety of scientists realized that it could be that quantum processes in the early universe, when the universe, like the balloon, was very small, could imprint, if you will, a message on the young universe. And then through this inflationary burst, the imprints of quantum physics could be smeared out across the sky, just like my little message gets smeared out across the surface of the balloon. Now that is a wonderfully exciting possibility. And I'd like to tell you a little bit about that because it's one of the spectacular recent successes in cosmology. And to do that, let me first show you a little bit about the quantum processes that take place on the very, very small scales. The key aspect of quantum physics that you need to understand to recognize what's going on here is a feature of quantum physics called quantum uncertainty, the uncertainty principle. And just to get a sense, how many people are familiar with the uncertainty principle? Wow, quite a few. Out of those, how many of you think you kind of pretty much understand what the uncertainty principle is about? Still, quite a few hands. Any of you with the hands that want to just come up, just give us a little brief thing on. No, it's difficult to explain the uncertainty principle in any detail in ordinary language, but I think for these purposes, the best way of thinking about it is this. Quantum uncertainty tells us that there are features of the microscopic realm that you just can't ever nail down with total precision. There are pairs of qualities of the microscopic realm, and if you understand one really well, its partner you don't understand at all. There's this quantum balancing act that comes from this fundamental uncertainty. And I like to summarize this uncertainty as telling us that the microscopic realm is kind of jittery, turbulent, chaotic, because these features are kind of fluctuating amongst all manner of possibility consistent with our limited understanding of what actually is going on there. So what I'd like to show you in this first sequence here is an impressionistic view of what the fabric of space would look like on very, very small scales when you take quantum uncertainty into account. Remember, Einstein told us space can warp and curve. Quantum theory comes along, and as we'll see in a moment, shows us that space can be really turbulent on the smallest of scales. So if you bring the lights down for a moment, and the way we'll do this, we'll start on the scales of the very big, the familiar scales where Einstein just said space has this nice gentle geometry, and we'll take a ride in this elevator. And this elevator will take us to ever smaller distance scales, factors of 10 smaller every step of the way, going through the scales of everyday life, down to the scales of atoms, and there you begin to see quantum uncertainty coming into view. You see the jittery behavior in the microscopic realm, but if we keep on going, much, much smaller than that, we find that the fabric of space is also subject to these quantum jitters. So way down on these really tiny distance scales, this, according to quantum physics, is what's happening to the spatial fabric, vibrating up and down, undulating, all sorts of chaotic things happening in the microscopic realm. Now, again, if we go from the small and we ride back up to the big, uncertainty gets smaller and smaller on macroscopic scales. That's why you and I don't see uncertainty in the world around us. So as you get larger and larger, the amount of uncertainty, while still there, gets smaller and smaller. And if you go through the scales of everyday life and on to the large scales of stars and galaxies, you do recover the nice, gentle, undulating free geometry on which Einstein based his ideas in relativity. But on those tiny scales, you see that quantum uncertainty gives this jittery characteristic to the spatial fabric itself. Now, bring the lights back up. What people realized is that if the universe went through this inflationary burst, those little jitters from the microscopic realm should in some sense be stretched out. And if they were stretched out, people realized through detailed calculations, those little jitters should affect the microwave background radiation that we were talking about a moment ago, this bath of photons, this bath of radiation left over from the Big Bang, would be affected by these quantum jitters. And the effect would be that the temperature of the radiation, according to the mathematics, should vary by about, a thousandth of a degree or so from one point in space to another. There should be a pattern of very tiny temperature differences. The average would be the same, about 2.7 degrees Kelvin. But over here it might be 2.7001. Over here it might be 2.6999. Tiny temperature differences. And people went out and measured those temperature differences. And indeed, this was first done by the Kolbe explorer, for which the Nobel Prize was won, more recently by something called the WMAP satellite. And when you look, here's what you find. This is a little map here where the red and blue regions represent tiny temperature differences, a little hotter, say, in the red, a little cooler in the blue. And the pattern of hot and cold spots on the sky, just measuring the temperature, in essence, putting a thermometer in space and measuring the temperature, aligns with exactly what the mathematics says when you put together quantum ideas with this inflationary burst. And I'd like to show you this one quantitatively in much of the way I did before for the background radiation itself, because again, I think it really shows you how cosmology at the frontier has become a quantitative science, when in the past it was just completely qualitative. So I'll show you in this next slide. Let me just describe what it is. This next slide will show you a mathematical analysis of the hot and cold spots on the sky. And again, you don't need to understand the details of the theoretical curve, but the impressive thing will be to look at how the experimental data that measure those tiny temperature differences, how that compares with what the theory predicts. So if you can bring the lights down, let's just take a look at that. So here's the theoretical curve coming from the mathematics of general relativity with this inflationary burst. And here are the observations. That is something to behold. If you were to ask me what I thought the most beautiful image in culture is, you're now looking at it. Think about what this image is telling us. We have a theoretical calculation of quantum processes happening 14 billion years ago. Quantum processes 14 billion years ago, stretched out by a purported inflationary burst, an incredible expansion of space that comes from the mathematics, predicting that when we look out into space, we should see these tiny temperature differences of about a thousandth or a 10,000th of a degree. Spectacular equipment is built that can measure such tiny temperature differences, satellite-borne instruments that have the capacity to measure such tiny differences, and the data agrees with the theory in this spectacular way. That, to me, is one of the most beautiful things that our society, our species, has really ever produced. So with this, we then wind up having, if you want, a picture of what the universe looks like that comes from the theoretical insights and also data from the Sloan Digital Sky Survey. So this is now real data that was gotten by dedicated measurements of galaxies throughout space. And the reason why it's in little slices is because they did very, very detailed observations along various planes throughout the universe. It's too much work to do the entire night sky. But these galaxies, over 1 million galaxies that this experiment has carefully plotted, allows us from, imagine we are in the center of this just to give an Earth view of the cosmos, allows us to have a picture of the universe where we recognize that as you go ever further away from the Earth, you're looking ever further back in time, back to the luminous red galaxies, and even beyond them, quasars, which will come into view right here. And finally, this cosmic microwave background radiation with the hot and cold spots that we were just describing can really be thought of as encircling this all. So this radiation that's been traveling to us for nearly 14 billion years is what we have now been able to not only understand theoretically, but measure, and the experiments and observation agree to absolutely fantastic accuracy. Now, if you want a still image of where then we have gotten, it would look something like this. So in the beginning, there is this inflationary burst where the universe undergoes this fantastic amount of expansion from a tiny, tiny primordial nugget here. It expands to this large size. You then have these quantum fluctuations stretched out, giving these tiny temperature differences. The universe continues to expand. These tiny temperature differences yield tiny differences in the density, which causes matter to clump up into galaxies, stars, and ultimately, here we are looking out into the cosmos, looking back into time, and we've been able to sort out a fantastically predictive understanding of how the universe has evolved. Now, this would be a wonderful story. You can bring the lights back up in its own right. But in the late 1990s, there was a very unexpected discovery, which in many ways has changed how a lot of us think about the universe. And that discovery was due to this guy over here, Saul Perlmutter, this guy over here, Brian Schmidt, also Adam Rees. And these were the heads of two groups who sought to determine a very important feature of the universe. If space is expanding today, as Hubble had shown that it is, and if all that funny business about anti-gravity early on had long since subsided, as the inflationary theory predicts, then even though things are expanding today, it should be ordinary attractive gravity that's pulling things back together. So just as if you take a ball and you throw it up in the air, it goes up, but it goes up ever more slowly, everybody believed that the universe should be expanding, but expanding ever more slowly. And these guys sought to figure out the degree to which the expansion was slowing. A very natural question, because if it's slowing a lot, it means that perhaps it'll one day stop expanding. If it's slowing just a little, maybe it will keep on expanding forever. So this is a real important question if you want to understand the far future of the universe. Now, these guys went about very detailed measurements of distant objects. Details don't matter, but supernova explosions that allow us to see far out in space and therefore way, way, way back in time. Again, the farther out you look, the further back in time you are seeing, because it takes light that much longer to reach you. And these guys, more or less at the same time, although, you know, there's a little healthy argumentation about it, I guess, came to a rather spectacular discovery. They found that the universe is not slowing down in its expansion at all. Their measurements showed that it is speeding up. The universe is undergoing accelerated expansion, as if you took that ball, you threw it up, and it goes up faster and faster and faster. Unexpected result. Now, how do you explain it? Well, the way I've set up this talk, perhaps you can make a suggestion for how to explain what's going on. Anybody? A cosmological constant. Maybe this idea that Einstein introduced a long time ago to create an outward push that would stabilize the universe, that Alan Guth in some way introduced again early on in the history of the universe to create a huge outward push, maybe today there's a residual cosmological constant that is exerting on the largest of distances an anti-gravity force that's driving things apart, making the universe expand faster and faster. And indeed, their observations, together with a huge number of other observations from different perspectives, have indeed come to the conclusion that the universe is accelerating. And the best explanation that we have for today, indeed, is that there is this cosmological constant. Now, what actually is it? Well, it's a kind of energy that suffuses space in a uniform way. It doesn't give off light, so we sometimes call it dark energy. The measurements show that there is this cosmological constant, or dark energy, suffusing space, which can give rise to this anti-gravity push. But the particular amount of dark energy, the particular amount of cosmological constant, is a really peculiar number. So when you actually look, that's what it is. I don't know if you can you see that number? That's about 10 to the minus 123. That's what the observations tell us. Now, the problem for us theorists is we can't really imagine a calculation using laws of physics that would yield that kind of number as the output. You know, we're used to numbers like 1, a half, a third. Sometimes it's not a third, maybe it's 0.2964397. But to do a calculation, you know, with pen and paper, and you're calculating away, and by the end it's 122 zeros and a 1, that is so beyond our experience with what the laws of physics can yield that many people scratched their head and said, how are we ever going to explain that? And this conundrum, this cosmological constant, from Einstein through Guth and now today, has led to what many believe is one of the most profound potential revolutions in our thinking about the universe, if indeed the following ideas turn out to be the case. And the ideas I'm referring to come from a combination of these two gentlemen right here. Andre Linde, Stanford; Steven Weinberg, Nobel laureate, University of Texas. And these folks, their collective work suggests the following picture. Andre Linde, also a pioneer with Guth of this inflationary universe. He studied the mathematics of inflationary cosmology and came to the conclusion that the inflationary burst that Guth had posited, that the observation seemed to confirm, he came to the conclusion that that burst need not be a one-time event. When he studied the mathematics of this inflationary cosmology, he found there might be a burst here, and then in some far-flung region, there might be a burst there. There might be many, many cosmological bursts, giving rise to many, many, many different bubble universes, of which ours is just one in this grand cosmic bubble bath. Now, that's an interesting picture in its own right. Steven Weinberg came along and realized the following. He said, look, if you're trying to explain this incredibly bizarre, tiny number, this 10 to the minus 123, this cosmological constant, he said, well, here is potentially one way of thinking about it. What if there are many universes, of which we are just one? And imagine that the cosmological constant, this number, varies from universe to universe. Different universes randomly have different values of this cosmological constant. Further, he said, imagine that there are a huge number of these universes. In fact, imagine that there are more than 10 to the 123 of these universes. Well, if you take the cosmological constant, you allow its value to randomly vary in a natural specified range, say between, 0 and 1, then if you have 10 to the 123 universes, you're almost guaranteed that one of them is going to have a cosmological constant as small as the one that we observe. And then you say to yourself, well, we're just in this particular universe. It's the one that we can survive in. And there's no explanation for this particular number, this cosmological constant. We just happen to live in that universe where this strange value is realized. Now, that's an interesting and strange set of ideas. It suggests this very different picture of reality, this picture that, for instance, we might draw something like this. You can bring the lights down for a second, if you would. So you can imagine all these different bubbles, This number, this cosmological parameter, varies from bubble to bubble, and we just happen to be in one where it takes that very small and strange value. And in many ways, I could actually end the conversation here, where this really is, in some sense, the frontier of our understanding or our thoughts about cosmology. You can bring the lights back up. But there's a natural way in which these ideas, in a very interesting way, tie into ideas of string theory that I and many others work on. And the question I have for you is, do you have patience to listen to about 10 more minutes? Or should we go? Okay. So, we're now, if you will, going beyond the frontier of cosmology. This is really the edge of a lot of people's thinking about cosmology. Now we're kind of peering over the edge into the even more speculative realm, which involves ideas that are completely untested from string theory. But let me just tell you a couple of features about this idea because it will tie in to this picture in a very interesting way. Now, where do the ideas of string theory come from? What's the motivation? Well, if you bring the lights down, it really goes back to that issue that I mentioned just a little while ago, which is if the universe is today expanding, if you run the cosmic film in reverse, the universe gets smaller and smaller and smaller. The universe kind of implodes in on itself. The galaxies get closer together as you head back in time. The stars get closer together. As we've described, it gets hotter, denser, ever more extreme. And as I briefly mentioned before, you can use Einstein's ideas and the refinements of Guth and company to understand the universe way back to a tiny fraction of a second after the beginning. But if you try to push all the way back to time zero, unfortunately what you get is this: noise, static, a complete lack of understanding of what happens at time zero, because ultimately the laws break down. So, bring the lights up for a second. The goal of string theory, one of the goals, is to try to find laws of physics that don't break down under any circumstance, no matter how extreme the conditions might be. And there is this approach that we are working on where you basically rewrite the rules of what constitutes the ordinary constituents of matter, which we think does give laws that don't break down. So let me just show you the basic idea of string theory again, if you could just briefly take the lights down for me. So the idea of string theory, in case you haven't encountered it before, is pretty simple. The idea is if you take any piece of matter, here randomly chosen to be a candle in a holder, and imagine examining this object on ever tinier scales, we all know that if you go small enough, you encounter molecules, atoms. Here you have an atom, neutrons and protons in the nucleus with electrons circling around. If you go inside the neutrons and protons, you've got quarks. This is where the conventional ideas stop. The new idea of string theory, hypothetical, is that inside these particles, if you could look closely enough, which we can't, but if we could, the idea is you'd find these little tiny vibrating filaments, little tiny vibrating strings, as we call them. And the idea is that the different vibrational patterns of these strings, much like the different vibrational patterns of a string on a violin produce different musical notes, the little vibrations of strings produce the different particles in the world around us. So all of the particles of nature, electrons, quarks, and so on, according to this way of thinking about things, it all comes, bring the lights back up, from these little strings and the repertoire of vibrations that they can execute. Now, if I was going through a whole discourse of string theory, I'd explain where this idea comes from and all of its wonderful features. But I just want to focus upon one characteristic of string theory that's quite relevant to this many-universe, this multiverse picture that I was describing a moment ago. And that feature relies upon a strange characteristic of string theory that many of you have heard of, know something about, which is the theory requires that our universe have more than 3 dimensions of space. Throughout all of the conversation tonight, we've been imagining space has left, right, back, forth, and up, down, the 3 dimensions of common experience. When we've been talking about the expansion of the universe, we've been talking about the expansion of that 3-dimensional arena. String theory comes along and says there's more than left, right, back, forth, and up, down. it says there are other directions, other independent directions, other independent dimensions beyond those that we have never seen. And the way it tries to explain, at least one way, that we haven't seen them, the explanation is, imagine that the extra dimensions, rather than being large and expansive like the ones that we see all around us, imagine that they're crumpled up and tiny, so small that we can't see them. Right? A good example is like, if you have a traffic cable. From far away it looks one-dimensional because you don't have the visual acuity to see that it has a circular dimension wrapped around it. But if you could zoom in, you would in fact see that there is a circular, curled up dimension. If like a little ant walking on the surface, you'd see that there's a circular dimension that you could walk around as well as walk along the length. A tiny dimension and a big dimension. In fact, let me just quickly show you a visual on that. So bring the lights down, please. So here is, in fact, a traffic cable looked at from far away, looking just like a line. You don't have the ability to see the circular part that wraps around it. But if you zoom in and, in fact, take the perspective of a little tiny ant, the ant can walk along the cable, but because it's so small, it can also walk around the cable. And I do hope you appreciate this visual because it took so long to get these ants to do this. But there you have it, a long dimension that's easy to see, a curled up dimension that is much harder to detect. Now let's take that analogy and actually apply it to the fabric of space itself. So again, imagine that this grid represents the 3 dimensions that we know about. I can only show 2 on a screen. Imagine we go smaller and smaller and smaller into the spatial fabric. String theory tells us, if the ideas are correct, that we should encounter tiny curled up dimensions in the spatial fabric. And they're so small that if we had an ultra microscopic ant walking around, it could walk in the big dimensions, the grid that you and I have access to, but the ant can also walk around the curled up dimensions because it's so small. Now, string theory doesn't say that you have a dimension wrapped up like a little circle. Rather, it says that the dimensions are wrapped up into more complicated shapes. They have a name. They're called Calabi-Yau shapes or Calabi-Yau manifolds. They're Ricci-flat, complex Kähler manifolds of vanishing first Chern class, but if that language offends you, just look at the picture. And here you see that there's this rich geometry associated with the curled up form for the extra dimensions. So if these ideas are correct, for instance, as you sweep your hand in front of your face, you're not just moving in the grid, you're also moving around these extra dimensions, except they're so tiny that you keep returning to your starting point over and over again, not even realizing that you took the journey at all. Now, bring the lights back up. I bring up this idea for the following reason. One of the main criticisms of string theory that you may have heard of is that it has difficulty making definitive predictions that people can go out and test to determine whether the theory is right or wrong. And that is a very valid criticism of our state of understanding of string theory. Let me just quickly tell you why we have the problem. It has to do with these extra dimensions. I showed you in that little video one form for the extra dimensions, all nicely curled up. But it turns out that there are many, many different shapes that are candidates for what the extra dimensions could look like. And the thing is, physics that we observe in the world around us turns out to be rather sensitively dependent on the exact shape of these tiny curled up dimensions. Different curled up dimensions, different sets of predictions. Now, when I said that there are a number of candidates for the form of the extra dimensions, that was an understatement. When we compile, if you will, a catalog of possible shapes for the extra dimensions, the catalog runs to at least 10 to the 500 entries. There are many possible forms for the extra dimensions, which seems to be a bit of a problem for string theory until you put it in the context that we have been developing here tonight, as people like Lenny Susskind have argued strenuously for. Remember, if you recall, about 10 minutes ago, we had this notion introduced by this Nobel laureate Steven Weinberg that if there were more than 10 to the 123 different universes, seems like a huge number, then there would be perhaps a very natural explanation of that number that has been measured, that tiny cosmological constant. The number varies across all the universes randomly. If you have 10 to the 123 universes, you're bound to have one as small as 10 to the minus 123. But how in the world do you ever come up with a theory that naturally gives rise to at least 10 to the 123 or more different possible universes? String theory. String theory naturally gives rise to the possibility of 10 to the 500 different universes. So if you take this idea of string theory and reinterpret it cosmologically, and imagine, if you will, that this image that we were looking at before is now, bubble by bubble, if you will, imagine that the extra dimensions take different shapes in each of these bubbles. Inflationary cosmology easily can give rise to 10 to the 500 bubbles, if not more. String theory can naturally populate each of those bubbles with a different universe in the sense of different physical properties, different values of the cosmological constant. And if that idea, if that collection of ideas is correct, then there's a natural union between inflationary cosmology and string theory in a way that, at the moment, gives us our only real possible explanation for this observed fact of this tiny, tiny number, this dark energy, this cosmological constant driving the expansion of space. Now, I emphasize what we're now talking about is highly speculative. We don't know if string theory is right or wrong. We don't know if this multiverse, this multi-universe picture is right or wrong. We're putting two things together, each of which is completely speculative, but through their marriage, we potentially get a way of explaining a concrete observational fact that has been determined in recent years, that the universe is expanding ever more quickly, that there is this dark energy, this cosmological constant that is forcing everything apart. Let me stop there. Thank you very much. So as Terry mentioned early on, should there be anything that wasn't clear, I'd be happy to address some questions. So, want to start over there?
Sure. And it relates to the kind of concept that your slide that's up there now presents, that with the various possible universes that could be produced under the combination of the cosmological theory and string theory, it appears there that they're side by side. But my understanding was perhaps not side by side, but coincident in the same space-time, or overlapping, perhaps. So my question is, if you have all these various cosmological constants of these different dimension-containing universes, some must be expanding faster, perhaps. Some are already contracting. Could you elaborate on that a little bit, please?
Well, sure. So there are various versions of the picture that I've drawn here that come out of various ways of realizing this many universes, multiverse picture. One indeed is close to the picture that I do have here, where all of the different bubbles are separate from each other and they're moving off in their own distinct, possibly never overlapping regions of space. There are other versions where some of the bubbles form within other bubbles. So you have bubble inside a bubble inside a bubble. That's another picture that naturally emerges from some ways of thinking about the theory. The conclusions that we've been trying to draw are largely independent of those details. As long as you have many universes, regardless of how they're stacked up next to one another, and if various numbers, such as this cosmological parameter, vary from universe to universe, and if you have enough of them, then there's a natural explanation for there at least being some that have the strange value that we observe. Shape of the extra dimensions based upon certain other physical observables in the world around us. So I quickly mentioned that there are numbers that are quite sensitive to the shape of the extra dimensions. Numbers like the mass of the electron, the masses of the quarks, the strength of the electromagnetic force, the strength of the nuclear forces, on and on. This list of numbers in a way that we don't understand with adequate fidelity today, but we do know in general principles, depends upon features of these extra dimensions. So for instance, when we understand the mathematical link between the geometry and those observable qualities, then in principle we'll have a nice dictionary between features of the world that can be observed and features of the geometry of the extra dimensions.
I have two simple questions. Maybe they're obvious, but I never quite understood it. If you have, the first one is about the Big Bang. Is the claim that as the Big Bang is happening, it's creating its own space as it goes along? Because if the space existed before the Big Bang, then where'd that space come from? That's the one question. The other question is, I never quite understood, why is it more useful to think of a light traveling straight in a curved space? Why is it more useful to think of that model than light being bent in a Cartesian space being bent by a big mass? Why is the first one the model that's been accepted? I don't quite see that.
Yeah, so the first question has to do with the Big Bang and the notion that I think many people naturally go toward, which is that if you're talking about an expanding universe, even in the imagery that I showed you, it would seem to suggest the universe is expanding into some pre-existing realm. Is there sort of some empty lot within which the universe expands? And the answer to that is no. It's much closer to the way that you were describing it. As the universe expands, or perhaps I should say in the beginning, if the universe is really small, there's nothing outside the universe. And as it expands, indeed, it is stretching its own spatial fabric or adding additional space, whichever language you like is adequate. And in that way, the universe grows, but it's not growing into an ambient environment. It's creating the very environment that it then fills. So that's a far better way of understanding what we mean by the expanding universe. Now, your second question was, why should we speak about light traveling along straight lines or shortest possible paths, if you allow me to use that language, in a curved environment, rather than light being bent in an ordinary manner, the way a baseball would be bent if it was flying by the sun? And frankly, both are acceptable ways of describing what happens out in the world. The reason why we tend to speak in the more geometrical way, a curved space, is largely because it allows us to bring to bear all the mathematics about curved spaces that were developed in the 1800s. In fact, Einstein went to that body of mathematics and through it was able to borrow concepts from the geometrical literature in order to write down the equations of general relativity. So basically, it allows you to encapsulate a whole lot of physics with some very well-defined mathematics. And that's largely why that's the language that we use.
Hi, my name is Dan Garreau, and I have a question that's...
Hi there, Dan.
Oh, hi, Dr. Greene. Maybe other people are wondering this question too, and I'm hoping you can break it down for us. I've read that for the Large Hadron Collider to create a black hole and destroy the Earth, hold on. The theory of relativity must be wrong, Hawking theory must be wrong, and a certain version of string theory must be right.
Everybody's trying to knock string theory in some way. So maybe we should quickly address this. So there is this idea of the Large Hadron Collider. You all know about it, this big accelerator underneath Geneva, that possibly in the collisions between protons going around this tunnel near the speed of light, there's this possibility that black holes could be formed. Now, first off, that's a very strange idea, right? When we think black holes, we usually think large astronomical bodies, stars collapsing under their own weight, way out there in space. So what's this idea of a little black hole? That comes right out of Einstein's work. You know, if you take the sun, you squeeze it down to 2 miles across, it becomes a black hole. You take the Earth, you squeeze it to ½ an inch across, it becomes a black hole. But if you take an orange and squeeze it to 10 to the minus 27 centimeters across, it becomes a black hole too. A small black hole with the mass of an orange, but it still is a black hole. So black holes can be small. So that idea is completely sensible. What can happen in CERN, at this Large Hadron Collider, is that when the protons collide, they can crush enough energy, enough matter, into a sufficiently small space, according to some ideas in string theory, that a black hole might form. Now, some of the concerns about this are that maybe this black hole then begins to suck up the environment. You know, Geneva gets sucked into the black hole. People are not that worried about Geneva, but, you know, maybe then Switzerland goes and, you know, rest of Europe. So there's definitely been some concern about this black hole.
How fast would it eat the Earth?
Well, here's the thing. I'm glad you asked that. So I'm very glad you asked that. And the things to bear in mind are this. Number one, and really going along the lines of the way you frame the question, let's first begin with the insights of Stephen Hawking from 1974, where he showed that black holes are actually not completely black. They can actually radiate a little bit of energy through the surface. And when they are tiny, his work showed that they'd radiate their energy, their mass, so quickly that a tiny black hole would live for such a tiny fraction of a second that it couldn't cause any mayhem at all. Now, when some people heard that, they said, well, what if Stephen Hawking was wrong? You know, what if black holes don't actually evaporate and it sticks around? What about that possibility? And there's a way to address that. And very solid scientists recognize that the following set of words can be turned into a very rigorous argument that there isn't anything to worry about, simply this. We are subject to collisions right now far in excess of the energy of the collisions at the Large Hadron Collider. Cosmic rays, basically protons, streaming through space, slam into our atmosphere with an energy much greater than the puny collisions that we're able to create at the Large Hadron Collider. And these collisions don't take place just in Earth's atmosphere. These particles hit the moon, they hit the other stars, other planets. So if these collisions could produce black holes which would then grow and eat up the ambient environment, we should see stars disappearing. We should see planets disappearing. It just doesn't happen. So there's nothing to worry about. We have withstood for billions of years collisions far in excess of the ones that we will be able to create in Geneva. Question up there.
Hello.
Hi there.
I wanted to ask you a question about the quantum jitters you were talking about, how when the universe expanded very quickly that the word you wrote on the balloon could be seen in the sky. And it matched the graph quite perfectly with what we had figured out it should be. How were we able to figure out what that should be if you were saying they're so very random and so difficult to figure out what's going on the quantum level? And if our basic physics breaks down at that level, how do we know that it matches perfectly when we shouldn't really know what you wrote there in the first place?
Good question. So, first of all, let me stress that where physics breaks down is at times even earlier than the physics that we need to make these calculations. So don't worry about the physics breaking down for this issue, but you do raise an interesting point, which is if these jitters are random, if there is sort of a probabilistic quality to them, how is it that we can make such refined predictions about what we can see? And that's a question which really transcends what we're talking about here. That goes to the heart of quantum mechanics. How can it be that in a theory that has these random qualities, you can make any predictions at all? And the way we make predictions is in the following sense. Although there is a lot of randomness, the math of quantum theory allows us to predict the probability that we'll get one outcome or another. Which means that if you do, for instance, an experiment in the laboratory over and over and over again, the same experiment 1,000 times, quantum theory might say, 65 times you should get this, 802 times you should get that, 12 times you should get this, and so forth. And then you do the experiment 1,000 times, and you compare the frequency of the observations that you attain with the frequencies that the math of quantum theory says you should get, and there's a spectacular agreement. We do a very similar thing here. It's a probabilistic calculation. You have this big sky with all possible values of these random fluctuations being spread out across the cosmos, and we can speak statistically about what those temperature variations should look like. We can't say right over there it should be 2.716. We can't say right over there should be 2.695. But we can say that if you look at the whole spectrum of temperature variations, it should break down according to this or that statistical pattern. And that's what you were seeing up on the screen. And that's where you are able to test quantum theory with spectacular agreement.
Thank you.
So this thing where the entire galaxy is expanding, how much will that affect us? Will like it get really cold or what?
Very good question. You know, it reminds me of that Woody Allen scene. Do you know the one I'm talking about? In the therapist's office, doesn't want to do his homework because of the expanding universe, you know. And the first thing to bear in mind is that when we talk about the expansion of the universe, a natural question that people ask, or at least are afraid to ask, is, well, if space is expanding, does that mean our galaxy is expanding? Language that you used. Does it mean that our distance from the sun is expanding? Does it mean that our bodies are expanding? Is every bit of space expanding? And then people say, well, if that were the case, how do we even know there's any expansion at all? Because our rulers would be expanding too, so there'd be no way to discern this expansion. And the thing to note is that the expansion only takes place on the largest of scales, where there aren't any other forces that can resist the expansion. Our bodies are not expanding because of the expansion of space. However much you might want to say, you know, 32 to 34, hey, it's the expansion of space. Yeah, that won't work. Just won't work. Because our bodies are held together by the electromagnetic force between the constituents that make us up, and that force is much stronger than the outward stretching of space. Our bodies can resist easily that outward stretching. So can the force between the Earth and the sun. We're not getting further from the sun because of this expansion. Similarly, the structure of the galaxy is not getting bigger either. The galaxy is holding together. The gravitational pull holds everything together, can resist that outward expansion. It's only when you look on scales much, much, much larger than even individual galaxies that the expansion takes place. Now, that would suggest that the expansion won't really affect us very much at all, at least not today. But let me talk about the far future, because that is a context where it can affect us. If indeed these ideas are correct and the universe is expanding ever more quickly, then the idea is that things that are away from us, that are moving away from us, sooner or later they're going to get so far away that there's no possibility for the light they emit to even reach us. We will lose sight of them permanently. Distant galaxies will disappear over the horizon, as we call it. Nearby galaxies will hold together gravitationally in some versions of this, but other versions, they'd be pushed away too. So there's a possibility that in the far, far, far future of the universe, if you're able to hang around, when you look out into the sky, it'll be very different. It'll be a very lonely place. There'll be no other galaxies nearby for us to look at.
I have another
Please.
question. It's kind of silly,
That's
but
okay.
I'm only 11 years old. How come when you showed us the pictures up there, the galaxies were like swirling around in a circle?
The galaxies, or
Not that picture, a different picture, but like the swirly white things, blobs, were going around and around. How come?
Yes, so I think I know the imagery that you have in mind, and I should confess that when you deal with graphic artists, they have a somewhat different agenda than we scientists do, and like to really strut their stuff. So they tend to inject this imagery with things that they're able to do simply because they are able to do it. But you should also bear in mind that our galaxy, the Milky Way galaxy, you know, it is much along the lines of the shape you saw there, a spiral, and the galaxy is rotating. So for instance, our sun is rotating around the center of the galaxy. The whole galaxy is spinning. So it's actually not a bad picture. It's not a great picture, but it's not a bad picture of what actually is going on. The key point of the image, though, was that if you run the cosmic film backward, things come together. That's the real message to take away from it.
Oh, all right.
Is that okay?
Yes,
Thank
thank
you.
you.
Hi.
What are the units of the Cosmo constant?
The units of the cosmological constant are energy density. So it's an energy that's spread through space, and we typically measure it by how much energy is in every cubic volume. And it's up to us which units we'd like to use. Now, the units I was using up on the board were the natural ones for a theory of gravity, theory of cosmology, so-called Planck units. And that's where, in those natural units, the ones that one should be using when one is doing analysis of cosmology and general relativity, that the number comes out unnaturally small. Is that...
Do you have SI?
Pardon me?
SI units? Like
say it again?
Kilograms per meter squared?
No, they're not SI units because, again, those are relevant for everyday scales, you know, meters and kilograms and seconds. When you're talking cosmologically, the units are very different. They are the Planck length, 10 to the minus 33 centimeters. They are the Planck time, 10 to the minus 43 seconds. They are the Planck density, which is, I don't know, about 10 to the 99 grams per cubic centimeter. So they're very strange in everyday units because those are the wrong units to be using. They're just not relevant. They're good here on Earth, but they're not really relevant to the cosmos.
Thank you.
Humans can already build quantum computers with few qubits. And in the future, these computers will be able to solve problems with exponential speedup. So some problems like Shor algorithm will be able to solve the problems of factorization of integers in a fraction of seconds that now we would need longer than the universe exists on the normal computer. There is also speculation that if the quantum mechanics is nonlinear, then P is equal NP, which would be a complete breakthrough in computer science. And I was always interested in this. If string theory will allow to build computers more powerful than quantum computers, at least in theory, and second, is there any chance that quantum mechanics is nonlinear?
No and no. So let me just elaborate for half a second. So string theory doesn't really give you any particular insights, at least as of today, into quantum computing. It embraces quantum mechanics without changing it, so all of the wonderful features of quantum mechanics that can be brought to bear in quantum computing would go through pretty much as if string theory didn't exist. And as far as your second question, which I did remember when I gave my answer no, I just can't remember what it was now. What was it? Anybody? What was the second question?
The question was, is it a possibility that quantum mechanics is nonlinear?
Could quantum mechanics be nonlinear? Yeah. No. There's no evidence for that. Every attempt to make quantum mechanics nonlinear has run afoul of making predictions that are wrong. Steven Weinberg, again, spent a lot of time trying to investigate nonlinear quantum mechanics. It just doesn't seem to bear fruit.
Question, is Steinhardt and Trick's ekpyrotic model of the universe still viable?
You know, it's viable. I don't find it myself particularly compelling. It's an interesting competitor to inflationary cosmology and is worthy of being spoken of. And if I had more time tonight, I would have spent a little bit of time talking about it. And it's a worthy competitor, but it has never convinced me that it really has the same kind of explanatory convincingness as inflationary cosmology. And that could be simply that I'm used to inflationary cosmology, I admit that, but it's never really grabbed hold of me.
Earlier you talked about how after the inflationary period people thought that gravity would slowly cause the universe to collapse back on itself. But if the universe is really space-time that was created through this inflation, and matter are really contents that move through space, what's the link that would cause a gravity attraction between the matter to have any effect on the universe expansion?
So again, when we talk about the expanding universe, you shouldn't think about it as matter moving through space. The matter is really not moving at all. The galaxies, if we use those as the markers of space, it's as if the galaxies are stitched into the spatial fabric, and it's just that the spatial fabric is stretching, and therefore it seems as though the galaxies are moving apart, and we use that language. But really what's going on is this spatial fabric is stretching. When we talk about gravity pulling things back together, what we really mean is that gravity tends to cause the spatial fabric itself to slow down in its expansion, and if there's no other force, gravity will pull the fabric and cause it to start contracting. And that's what we mean by the galaxies coming back together. Not that they're going to move through space, but the space itself will collapse, yielding the reverse of a Big Bang, which we call a Big Crunch.
So you're saying then that the gravity is not a force necessarily between matter, but it's a force integral to the universe itself?
Well, I would even go further. When you really embrace Einstein's ideas fully, you think about gravity as nothing but what happens to the spatial fabric. So we've learned from Einstein that ordinary gravity can be thought about spatial fabric that's warped, and I showed you a visual of that early on. That's why the Earth goes around the sun, because of the shape of the spatial fabric. Similarly, gravity manifests itself in other ways cosmologically within properties of the spatial fabric. The spatial fabric can stretch or contract. In common language, it would be an anti-gravity push or an attractive gravity pull, but the more precise way of talking about it would be attractive gravity causes the spatial fabric to shrink, the repulsive gravity causes it to expand.
In your discussion of quantum fluctuations, which you also refer to as quantum foam, you're saying there's evidence in the background radiation that this really has occurred. However, in your most excellent book, you talk that this quantum foam only occurs when you are less than a Planck length. However, you also say that you can't really get below a Planck length because that's really an inaccessible distance. So I'm sort of confused how you can have quantum foam exist at all when you can't really get below a Planck length.
Yeah, so you may recall, I'm not sure which book you're referring to, but, oh, that one over there, The Elegant Universe?
Yeah.
Ah, don't listen to The Elegant Universe. No, in The Elegant Universe, chapter 5, if you look in chapter 5, yes, chapter 5, there's this picture of what we call the spatial foam, which is the quantum foam, where we zoom in on the spatial fabric and it gets to a point where it's all hectic and chaotic. However, if you look at other layers in that diagram carefully enough, you will see that they too have a certain amount of undulating characteristic from quantum physics associated with them. All I've spoken about here tonight was those layers that are larger than the Planck length. I've not gone to the Planck length. I would have if this was a lecture about string theory and where it comes from, but that's not my intent. So my intent was to talk about ordinary quantum physics in a domain that we understand well, much larger than the Planck scale. You still have these jitters. They're not as violent as they would be at the Planck scale. They're completely under control to the point where we can do calculations, and you saw the outcome of those calculations and how they agree with observation.
Thank you.
3 more, I'm being told.
Hi, well, I have a couple questions.
Ooh, we're going to exhaust them all right here, I think.
Well, I can only give one if you want.
Whatever you'd like.
Well, I heard somewhere that, well, I don't heard somewhere, I'm pretty sure that strings have like 10 or 11 dimensions depending on which theory you look at. And if 3 of those are space and there's maybe 1 of time, then what are the other ones?
Yes. And I think the best way of thinking about the other ones is that they're really, in some sense, no different in terms of their fundamental stuff than the dimensions we see around here. The only real difference is that rather than being large and expansive, as this one is, or that one is, or this one is, they're just smaller. So if you may recall the visual that I showed you, we went way down into the spatial fabric and we saw these curled up dimensions. They're made of the same spatial stuff, if you will, as space around us. They just have a different shape, tightly curled up and small rather than big and unfurled.
All right, thank you.
Is that okay?
Yeah.
Okay.
It makes sense, a little sense.
So if all of the universes were expanding at different rates with different physics rules, then what would happen if a universe was expanding so quickly, like quicker than space, that was pulling it apart from another universe? What would happen if they collided?
Yes, so an important question is what does happen when these bubble universes collide? And there has been a tremendous amount of work on that, and we understand fairly well the kinds of features that a universe would acquire if it were bumped into by another one of these bubbles. In fact, one of the early problems with these ideas was the features would differ drastically from anything that we see in the world around us, suggesting either that somehow you better ensure that the collisions don't happen or the theory is wrong. Now, there are other variations of this theme that are understood more recently where the bubbles are all expanding, but the space in between the bubbles is expanding even faster than they are. I like to think of it using a metaphor of Swiss cheese. And imagine that the holes in the Swiss cheese are the different universes, and imagine that the meat of the Swiss cheese. I don't like that language. I'm a vegan. I don't even like cheese, from that matter. This is making me very uncomfortable, this whole conversation. But anyway, let's just finish it. So the cheesy part of the cheese, right? That part is expanding much more quickly than the holes are expanding. And if that were the case, then these bubbles typically wouldn't collide. And that's a version that many people study. Are we going to do one more? Is that it? One last one? Yes, over there.
Yes, when you were talking about string theory and that the smallest known particles, when you try to divide them further, become like little teensy string-like things that vibrate.
Yes.
And somehow different substances vibrate in different ways.
That's right.
Okay, I had the thought when you were saying that, not that I'm an expert, but the little I know about it, that is very similar to the way homeopathic medicine, it's one of the principles of it, and it's how it works. And I was thinking that maybe, therefore, string theory would predict that that's how it would work, and that maybe you could even sort of prove it in a certain way by studying the relationship between the two of them. So I just wondered if anyone had ever studied that.
Yeah, you know, it's a natural thing that many people are inspired to do, to try to link some of the ideas at the cutting edge of forefront research with other things in the world around us that they might believe in or want to believe in, for which they don't have a physics explanation. And this is an example of that, which is a very natural one to pursue, but it's very, very hard to see how that link could ever be made, even irrespective of one's view of homeopathic medicine. I know there's a wide range of perspectives. Regardless of what you think about it, what we are talking about in string theory is taking place in such a fantastically small scale, 10 to the minus 35 meters, that it's so small compared to the phenomenon for which you're seeking an explanation, which happens on the scales of everyday life, that bridging that fantastically huge gap is something that is so far beyond what we can do that there's nothing that we can say that is really sensible. I mean, I'm tempted to go further, but I don't think I will. So let me just end it there. So it's very, very difficult to bridge the gap from the ultra microscopic with anything directly observable in the world around us. So, thank you very much.